today's topic is about operation of the grids. And we are honored to have Dr. Elizabeth Ratnam, the senior lecturer and senior research fellow at the Australian National University to share with us this topic today. Dr. Ratnam has extensive research experience and expertise in electricity, especially operation of grids, and she has also work experience in the industry. So I'm sure that she has a lot to share with us today on this topic. And it will be very interesting to know, because we've been discussing about the potential and the need for having more renewable energy in the grid. And we also discuss about the difficulties, the obstacles in many countries, especially in Indonesia, Vietnam, and the Philippines. So today you will find more answers to the questions that we've been discussing in previous session. And we will have Tarek to facilitate the sessions when it comes to Q&A. So without further ado, I would like to introduce Dr. Elizabeth Ratnam, and over to you, please.
Thank you very much for the kind and warm welcome and introduction thing, and delighted to be here with you all today. If you just give me one moment, I'll share my slides and my screen and just confirm that you can all see everything. So if I first start with sharing my screen, and then I share my slides, and I'll just rearrange my Zoom so everyone can see that okay? Okay, thumbs up, perfect. Okay, so let's get started. So welcome to session 6, the operation of electricity grids. I'm Dr. Elizabeth Ratnam, and in this session we'll explore ways to operate electricity grids with rooftop solar, battery storage, electric vehicles, and we will consider microgrid operations. Furthermore, in this session, we'll consider ways to leverage existing sensor technology, including smart meters, and the opportunity for new grid sensors, such as micro-synchrophasers. More specifically, we'll explore the operation of electricity grids with micro-synchrophasers in the context of adaptive islanding or otherwise resilient microgrid operations. Throughout, we will focus on opportunities to balance both the customer and the utility benefits of operating electricity grids with renewable and distributed energy resources. Lastly, I'll introduce a new operational strategy for microgrids to enable socially resilient electricity pricing. Please do come prepared with questions, and we'll pause along the way for any Q&A. Thanks, everyone. Okay, so to get started, over the next few minutes, I'll tell you about the green box. But first, how many times a day do you flick a light switch? Today, most of our electricity comes from burning coal at a power station in Australia. So when we turn this light on, we indirectly emit carbon pollution, which contributes to climate change, a serious threat to our environment. In response to climate change, many governments around the world are subsidising homeowners who install rooftop solar panels. In Australia, a commonly known subsidy is the feed-in tariff, where customers are paid for the solar energy they produce. Now imagine you install rooftop solar and they generate enough electricity to cover all of your energy needs with a little left over. You go to work and it's a nice sunny day, so your solar panels are doing a great job. But no one is at home using your solar electricity. And your neighbours are at work too, so they aren't using your solar electricity. So where does your solar energy go? Unfortunately, if no one is using your solar energy, the energy you produce will be wasted. This is because the physics of the grid will cause the voltage at the solar inverter to rise. And for safety reasons, your solar inverter will switch off. But there is an alternative to switching off your solar inverter to prevent the waste of solar electricity. In my research, I combine battery storage with the solar panels so that the solar energy produced in the daytime is stored and delivered to you or your neighbours when needed. In the picture, the arrows illustrate the direction electricity can flow, and the green box controls these power flows. Specifically, the green box determines if your solar energy is stored in a battery, is used to turn your lights on, or is fed back into the grid for your neighbours to use. In cases of widespread power blackouts caused by natural emergencies, my green box also keeps the lights on along your street. The benefit is community-wide resilience to power blackouts. To design the green box, I use mathematical optimization with objective functions formulated to not only accelerate the grid integration of solar PV, but also with the perspective of creating a resilient, carbon neutral electricity grid. So now let's zoom out and consider elements supporting the creation of a resilient carbon neutral electricity grid. Elements include microgrid control and operations, the interaction with other microgrids, weather forecasting, energy markets, electric vehicles, wind turbines, solar PV, and battery storage. In the first part of this presentation, I'll focus on the solar PV and battery storage in a residential setting. So let's provide some important background information on PV generation today and the challenges for grid integrating the solar resource. Traditionally, distribution grids were designed for one-way power flow from the generator to the customer, with operators monitoring and remotely controlling the grid. Actuation has been limited to opening and closing switches, tap changing transformers, and switching in capacitors. And as a last resort, switching off the load. Recently, there's been a rapid uptake in rooftop solar PV around the globe. In Australia, there is now more than 15 gigawatts of installed PV. And with a population of 25 million, this translates to each person owning approximately 2 solar panels or 3.8 square meters of solar PV. Australia is not too far behind Germany in this kilowatt per person metric, particularly when you consider that just 2 to 3 years ago, Australia had approximately 1 panel per person and Germany had the equivalent of 2 panels per person. That is, PV installations in Australia have more than doubled over the last 2 to 3 years. So how do we integrate this PV generation into the electricity grid? On the left, we see a daily demand profile for 26,000 Australian residential customers. All of these customers have installed solar PV with a peak combined generation output of 36 megawatts. On the right, we see the impact of the demand curve as a consequence of the solar PV generation. Specifically, the green shaded area is the new solar PV generation, and consequently, the grid demand at midday approaches 0 megawatts. This new demand curve is commonly referred to as the duck curve, as the midday dip follows the curve of a duck's back. From the utilities perspective, this new duck curve is not particularly helpful. Instead, it potentially creates new problems for the grid to manage. That is, during the midday period, the voltage on the grid may rise if the PV generation is in excess of the customer load, creating reverse power flows on the grid. If this voltage rises too high, the PV inverters may switch off for safety reasons. That is, we might waste the solar energy we produce. From the utilities perspective, if we can move the excess generation from midday to the late afternoon or evening, we can potentially alleviate congestion on the grid, which might otherwise create a need for grid expansion. Now let's zoom into a single residential customer located in Australia. The average customer's load is 20 kilowatt hours a day, which costs on average $5 per day. If this customer installs a small solar PV array that produces 5 kilowatt hours per day, the customer potentially saves $2 a day and will export 2 kilowatt hours per day back to the grid, contributing to the duck curve we just seen. Instead of exporting the excess PV generation back into the grid, what might be an alternative solution? So anyone want to chime in and consider different solutions to helping the grid in this context. Instead of exporting the energy back to the grid, what might be an alternative solution to doing that?
If you feel free to put your suggestion in the chat box if you can, or if you want to raise your hand, we can unmute you to make a comment. Does anyone have any suggestion? Okay, a few suggestions are coming in about storage. Elizabeth, put up a storage system or storing the energy.
Wonderful.
A local battery.
Yeah, so there's many kinds of storage, right? So battery storage is one kind of energy storage system. Any takers for other kinds of energy storage systems? So hot water energy storage. So that's something we've been doing for a very long time, right? We heat the hot water and then we use it at a different time. So for example, we could heat our hot water systems when we've got this excess solar energy and use that hot water later in the evening when we have showers or baths, for example. That's another kind of energy storage. Any takers? So we have battery storage. What kind of battery storage systems could we consider? Any takers for that one?
Any ideas about kinds of batteries? There are some other types of storage in there that are mentioned, Elizabeth.
Oh, fantastic.
Hydrogen, pumped hydro storage was mentioned as well.
Awesome. Flywheels. Anyone heard of flywheels? There's a really neat company in California selling flywheels for large industry sort of customers. But that's a mechanical energy storage technique. But in terms of battery storage, if I'm at a residential setting, two common types of energy storage systems come to mind. Anyone want to comment on those two types? So we could have stationary energy storage like the Tesla Powerwall. I don't know if hands up if you've heard of Tesla Powerwalls. Have we got hands up happening? Has anyone heard of them? There's a bunch of awesome, interesting companies that do battery storage across the globe. B-Box is one, and there's also DC battery storage from an ANU startup that is across most of, I think, Indonesia and Thailand and Vietnam, which are doing remote rural locations of battery storage. But other than battery storage, the second one that comes to mind, I don't know if it's come through the chat yet, is electric vehicles, right? It's a portable energy storage device. So we could just charge them and then it becomes a load. Or some of the new electric vehicles on the market, and they enable us to charge and discharge them so that they can support the grid in this way. Anything else that popped up before we move on?
Yeah, one other thing that's popped up that's quite interesting, Elizabeth, is about the load itself. So someone suggested, shifting the household power load from night to daytime, so demand management and consume electricity more. And they gave the example, for example, of how you do your laundry, doing that in the daytime, not in the evening.
Absolutely. And if we can match our demand to our generation, we don't even need energy storage, right? That's a really excellent point, and something we'll touch on a bit later through the presentation, because it sort of pops up of like why customers might not be financially benefit from energy storage, right? If they're already doing good things like using the generation to minimize their loads when it's available. Okay, so shall we move on? Anything else before I move forward? Yep, right to go? Or yep, okay. Okay, so let's go back to our single residential customer. The black curve here is the average load profile across a day, and the gray curve is the average solar PV generation output. And the red shaded area is the excess PV generation that is pushed back into the grid. The vertical lines here denote the time of use pricing transitions, which we'll formalize a little later. Now, in response to the question of what might we do with the excess generation, we'll ask questions like, what happens if we store this in a battery? Which leads us to questions like, 1, is this cost effective? And 2, what is the optimal use of the battery? Before exploring these questions, I'd like to do two things. First, I'd like to acknowledge my collaborators here, Professors Stephen Weller, Chris Kellett, Jan Kaleisel, and Oyten and Vahid, who were my colleagues at the University of California, San Diego. And next, I'd like, in the remaining part of my session today, I'll explore ways to coordinate residential systems with and without plug-in electric vehicles, and I'll introduce new control paradigms termed phaser-based control, and we'll touch on resilient electricity pricing in the context of the Texas power outage that happened earlier last year. So towards the end of our session, I'll revisit the red question mark here, but first, let's recall the average customer's load is 20 kilowatt hours a day, which costs on average $5 per day. If this customer installs a small solar PV array that produces 5 kilowatt hours per day, the customer potentially saves $2 a day and will export 2 kilowatt hours per day back to the grid, contributing to the duck curve. Instead of exporting the excess PV generation back into the grid, what might be the benefit of storing it in a battery? To answer such questions, I'll need to introduce some notation, but please don't feel the need to remember the notation, and I'll introduce it as I go. The key thing here is that we're looking at average power flows over short intervals of time, say 30 minutes. Here, delta denotes the length of the time interval, 30 minutes, and K is the index for the time interval. So for example, if we're looking at a 24-hour period, we'd have 48 30-minute intervals in that period. So K would be 48 and delta would be 30 minutes. In the figure, we depict the point of common coupling between the distribution grid and the residential customer. From here, we have a meter, which we denote by M, which measures and records the power flow X2. E to B and E to C are the prices for buying and selling electricity back to the grid. L is the power consumed by the customer. X1 is the power to and from the battery, and G is the power from the PV array, the solar array. The arrows illustrate the direction of positive power flow. So in this picture, hands up if you can identify where we might have two-way power flows in this picture. Anyone want to hazard a guess where we will have power to and from? Either we've got the solar, the load, sorry, yep.
Suggestion has come in that it's in the box M.
The box M, the meter, yes. So we'll have power to and from the meter, correct. There's one more. Anyone else want to hazard a guess where we have two-way power flows? The battery, sorry. So the battery can store energy or it can push energy back out, right? So it's sending energy in both directions. The load is traditionally one way, right? We turn appliances on, we flick switches, we turn fridges on, things like that. So that's our load. And PV generation is one way, right? So a little fun fact, I guess, on the side, we would expect energy from the solar array when there's sunlight, right? But if you have some really strong street lighting, you might actually find a small amount of energy being produced in the evening from the solar array if you have a very strong street light. But that is uncommon, but I have observed it and it threw me for a little bit. So it's not impossible, but very small and not really considered enough energy to have a large impact. So we would expect one-way power flow from the solar PV during daylight hours, and we would expect the energy from the solar array to peak at what time? Any guesses at what time the solar energy will peak?
When would be the peak for solar production?
Any suggestions?
We get some suggestions coming in: 11 to 1, 10 to 2, sort of that midday period, I think, middle of the day period.
Absolutely, great. So we're all on the same page. The other little fun fact I'll sort of talk about a little bit here, we've got a meter M, So in the early days before smart meters, we had electromechanical meters. And with these meters, we could actually incentivize solar PV. So the meter, it's not a smart meter, so it can't digitally record how much energy is coming or going. So how did we incentivize? Anyone has it a guess, I guess. We'll talk about that a bit later, but is there any takers for how we could provide incentives for solar PV when we had the old electromechanical meters? And if there's no answers, that's great, because I'll be talking about it very shortly. Any takers?
No answers at the moment, I think, Elizabeth.
Okay, fantastic. We'll touch on this a bit later, but the answer is net metering. So the electromechanical meters, when the energy was going back into the grid, they will wind back, right? So instead of your meter ticking always up, because you're consuming load, with solar energy, it would actually go in the reverse direction. And so net metering is one of the very earliest forms of incentives for solar PV, and it can still be deployed today if we don't have things like smart meters, which aren't widely deployed across the globe. But in that context, we'll focus on this particular policy today because it is applicable, I guess, to anywhere that has a meter, whether it's electromechanical or if it's a smart meter.
Actually, one colleague, Elizabeth, from Indonesia did mention net metering just before you started talking. So,
fantastic. Yay. Well done. Okay, so we have some people that are familiar with this. Okay, so now let's go to our next slide. Again, we don't need to remember the notation here. I'll introduce it as I go. But the key thing to note here is that we drop the index K when defining the day ahead profiles. So from the picture, L here is the day ahead load profile, and G is the day ahead generation profile. And remember, LK was the load profile for a 30-minute interval, and now L here is the load over an entire day, right? So we're looking at a day, not a short interval of time. And so we also here introduced some new terms, some energy, in particular energy savings, which is what we define as the difference between energy bills with and without a battery over the course of a day. So when we're looking at the financial benefits, we benchmark the savings by having by your bill if you did not have a battery compared to your bill if you did have a battery. And before we just move on, I'll introduce it a bit later too, but I just want to sort of see if anyone's aware or familiar with the term time of use pricing. Any hands up if you've heard of the term time of use pricing?
Is that something we see in Philippines, Indonesia, or Vietnam, time of use pricing? Would anyone like to?
Oh, I see a hand up.
Yes, if we could unmute Ahmed. Ahmed, you want to jump in on time of use pricing?
Okay, thank you. Hi, Elizabeth. I'm Ahmad from Indonesia. So I think time use pricing is kind of differentiate of what we call electricity bill based on the time itself. When the peak load of the power system, then the price is higher, and when the load is lower, then the price of the electricity will and then become lower as well. Like that. So when we differentiate, we have to like dynamic pricing of because of the time use pricing itself. We then drive the users, the customers, to prefer to use the electricity in the lower price at that time. So it can also correct our load factor itself of the system.
Spot on. Yes. You're just dropping a bit faint at the end there. Was there anything else that I missed? Or I think that was an excellent description of time of use pricing. And so the reason I sort of pointed out now, and I will reiterate it as we go, is that time of use pricing was what actually motivated Australia to move to smart metering. And so with the electromechanical relays, we could incentivize solar PV, but we couldn't differentiate the prices at different points in time. And people that have worked in utilities probably are well aware of this, but usually our peak loads, particularly in the early 2000s when we were introducing smart meters, happened for about half an hour to maybe 2 hours over an entire year. And this half an hour to 2 hours of load would drive millions of dollars of capital expenditure. And so time of use pricing was an incentive program that was facilitated by smart meters to try and shift this 1 day a year, this 2 hours of load, so that customers would reduce their energy at that particular peak pricing period. But it was deployed every day of the year. And what we found was that there was a bit of customer fatigue, like customers modified their behavior when they used energy with time of use pricing for maybe a couple of months. But usually that 1 day a year that was super hot with the peak pricing, it wasn't enough of an incentive for customers to not turn their air conditioner on, for example, which was driving our peak, because it's the hottest day of the year. It's 40+ degrees in Australia, and I bought an air conditioner, so that's the 1 day I'm going to use it, right? So this time of use pricing wasn't particularly successful for shifting our peak loads, but what it did enable was a market for battery storage, which we'll touch on a bit later. So all of the energy storage suppliers around the globe sort of came to Australia first, because we were one of the few countries that had this time differential pricing, which was originally deployed to change people's behavior to reduce our peak loads. But what it actually was really successful at doing was providing financial benefits to customers who wanted to install battery storage. Okay, so let's move on, and I'll reiterate this as I go. I just wanted to sort of give a little bit of history and context there in the context of electromechanical relays. Okay, so now our approach is to consider the benefits of residential battery storage in the context of financial policies such as net metering and feed-in tariffs, when customers are billed according to the time that they use electricity. So in the figure, we overlay the time of use tariffs as published by Ausgrid, one of the largest electric utilities in Australia, and we see the shoulder pricing period together with the peak pricing period coincides with the excess solar PV generation. So remember, this time of use pricing was designed to reduce peak loads, not to facilitate or encourage solar PV uptake, right? The feed-in tariffs were designed to do that. So if we shift the red shaded area, that is the excess PV generation, to the peak pricing period, we ask the question of how much money might we save? And so here we see the peak pricing period at Ausgrid was between 2 and 8 p.m. The shoulder pricing period was from 8 p.m. to 10 p.m. and 7 a.m. to 2 p.m. And the off-peak pricing period was from 10 p.m. to 7 a.m. Maybe we'll introduce this fun fact a bit later, but I'll just plant the seed of the question. Why, like we have an off-peak pricing between 10 p.m. and 7 a.m., but often in the utility Ausgrid, we would see the peak load for residential customers occur during this period. Anyone want to hazard a guess of what would create this peak load? And why we weren't concerned about it, why we didn't make the price higher? So we touched on it a little bit before. Is there answers in the Q&A?
Not right now, Elizabeth, but I think if anyone wants to answer, the question is why is a peak load sometimes occurring in the off-peak period, and why is that not a concern?
Okay, so hot water systems, they're usually about 40% of the energy of a customer in Australia. So 40% of the energy is hot water, but hot water, as we discussed, is a form of energy storage, right? So we can heat up the hot water overnight and then use it through the day. We don't actually have to use it at the same time that it's heated. And so we have incentive programs for this controllable load, so that the customers use their energy, heat up their hot water systems at night. But because it's 40% of the load, the utility had to actually stagger the time at which these hot water systems turn on. And so if you're looking at one particular urban area, like a suburb, for example, they all might turn on their hot water systems at, say, midnight, and then the suburb across might all turn on their hot water systems at 1 a.m. and they'll stagger it in this way. So if you look at the load peaking for that particular suburb, you'll see it will peak because of everyone turning on their hot water system at the same time. But if you look at geographically across a region, you won't see the peak occurring at midnight because they'll all be staggered at different times. And so I just want to plant the seed that we often do see peaks. They're often not too concerning, one, because they're staggered, two, because it's usually cooler at night, so we get more thermal capacity out of our network. And three, if there was an issue, for example, with loads, the utility has control of those to move it to a different point in time. So I just want to plant that seed because we'll see some of this hot water peak later on in the slide deck. Okay, so as we can see here, going back to the picture, we've got the red shaded excess energy. And we're looking at what is the financial benefit if we move that energy to the peak pricing period so that we're using less load from the utility during that time. Okay, so before we answer this question, let's first look at the case where it's not cost effective to install a battery. Anyone want to hazard a guess of when and what scenario or what considerations it might not make sense for a customer to install battery storage? We sort of touched on it earlier before. Do we have any takers?
Not for right now, Elizabeth. There's a few suggestions to your earlier question that have come through. But
okay.
Yeah.
So I'll keep going. Perfect. Okay, so it doesn't make sense to buy a battery storage. Let's see when that's the case. So specifically, if the price for buying electricity is the same for selling electricity and there's no change in price across a day, then no battery is going to make you money, assuming you don't experience any inverter disconnection due to voltage rise. Okay, so we need some price to change throughout the day to make money. And in Australia, as I mentioned before, we have some time of use tariffs which support this opportunity to profit from energy storage. So that's some good news. And if you want to go through the math and you like that, there's a paper here and a lemma with a proof in the slides in the paper, which is highlighted, that you can work through that. But essentially we need, the essence of the message is that we need some time differential in price or some difference in buying and selling in order to profit from energy storage. We can't just have a flat tariff with net metering, for example, no price differential. So if you have the electromechanical relay, you have net metering. It's really not a meter that would facilitate customers profiting from battery storage because we don't have the ability to change the price with time. Okay, so now let's consider the financial policy of net metering, defined by a resident being billed at the same rate they're compensated for excess generation. And for this case, we assume that prices can vary throughout the day. Then simply, the energy bill with a battery is the price of electricity in dollars per kilowatt hour, multiplied by the electricity you use in kilowatt hours. That is, E to B here is multiplied by X2, which is multiplied by the time interval delta, which is 30 minutes. So the energy bill is just with the battery is the price for electricity, which is billed in dollars per kilowatt hour, multiplied by the electricity you use. So here the notation X2 is the sum of the solar PV generation, the power delivered from the battery, and the negative load delivered to the house as per the power balance equation. But note here, the only controllable thing is our battery. So do we really need to know our day ahead solar PV generation, so what generation we're going to get in the day ahead, and our load profile to make money by scheduling the battery? Anyone want to hands up if you agree you need to predict everything to make money? And I guess thumbs up. Is there a thumbs up if you think the opposite, that you don't need to predict the day ahead load and PV generation? Oh, we've got both. Okay, hands up. Okay, so hands up is that we need to predict late day ahead load and PV generation.
Yep.
Yep. And thumbs up is if we don't need to predict the day ahead load and PV generation. Have you got any thumbs up?
I see two thumbs up and one hands up.
Okay, great.
2 and 2 now, so it's
it's a
three,
little
3 hands up, 3 thumbs up. A clapping as well. We've got a clapping in there.
clapping. So it's not an easy thing to answer, and it's not a trivial thing to prove, but the next slide will go into the answer for that. So we've got all of everyone's answers set in. Last chance. Thumbs up. Was it? Hands up if you do need to predict the day ahead load, and thumbs up if you don't need to predict the day ahead load and PV generation. Okay, let's go to the next slide. Okay, so to answer this, let's look at the problem in another way. Instead, let's ask the question of how do we benefit from battery storage? Here, we'll look at the difference of the energy bill with and without a battery. And with some simple math, we see that the profit is dependent on just the power delivered to and from the battery. That is, the profit is directly calculated from X1 and the price for electricity, which is eta, where eta is equal to E to B is equal to E to C. So we've got the net metering policy in place, and the time interval is delta. So the good news is that with this new formulation, that we don't need to predict the solar PV generation and the load power to schedule the battery to make a profit. So we don't need to do any forecasts at all, really, because we can control the battery. We just say when to charge and discharge, and we have the price. And that kind of makes intuitive sense, right? So if you have this time of use tariff that changes with time, we want to charge up the battery when the price is really low, so the off-peak pricing period, and we want to discharge the battery when the price is really high so that we don't draw power from the grid. And so we can just follow the time of use tariff and charge and discharge the battery, and we'll make the most amount of money possible without needing to do any prediction of solar or load, which is really great, but not intuitive. However, this leads us to the next question of, is this a good thing to do for the grid? So is it good to not even consider someone's load and PV generation, just to take the price and charge and discharge the battery based on the price? Any takers for when that might not be a good thing to do for the grid?
Maybe we could use the same system. If you have a hands up, you think it might not be good for the grid at times. And if you put a thumbs up, you think it could be good for the grid. And we might invite a hands up representative and a thumbs up representative to comment on that.
So we've got hands up for it's a good thing for the grid, is that right? And a thumbs up if it's not a good thing.
Anyone want to put a hand or a thumb up? Encourage everybody to do so.
So repeat, hands up if it's a good thing to do for the grid, to just charge and discharge your battery based on a price. And a thumbs up if you think it might not be a good thing to do. Okay, I see a few hands up there. Yep. Should we invite someone from a hands up? Do you want to have a go?
And any colleagues with a hands up want to explain your thinking? You can see Angelus or Setuan. Angelis, would you like to have a go? We might need to unmute Angelis, please. Okay, maybe that was a technical issue there. We didn't get that working, Elizabeth, but
no. Shall I keep going, or shall we? Yep. Okay. And feel free to pop it in the chat window as we're going. And the good news is there's no right or wrong answer to this, right? And so if there's only a few people with battery storage, then absolutely the time of use tariff works well. There's a peak pricing period where there's congestion, and we should discharge all the batteries. The problem becomes when everyone has battery storage, or we have a big population of people with energy storage, and they're all doing the same thing. And so we'll get to this sort of point a little later, but I just want to reiterate it because it's the challenge with the grid in general is we want to create diversity. So it's the same as traffic. So if everyone finishes work at 5 or 6 and then drives home, we're going to get a lot of congestion on the road, right, at that period of time. The same thing happens in the electricity grid. So if everyone's discharging their battery at the same time, then we're going to create a new point of congestion in the electricity grid. And so if there's only a few people and we stagger the end times for work, then we can manage the power flow to reduce the congestion. And the same thing with energy storage. So diversity in what people do and behavior or controlling different devices. It's when we introduce policies, we need to be very mindful of what we're doing to the diversity. So if there's a small population, then that improves diversity. But if there's a large population, then we potentially create a new problem for the grid. Okay, I'll now move on to the next slide. Okay, so to answer such questions of is this a good thing to do for the grid, we propose a linear program to maximize the customer savings. Here, our objective function is formulated to maximize the savings as previously formulated, where we include the battery constraints. So if we have a 10 kilowatt hour battery, and we observe that all customers will save $988 per year when following a time of use tariff as published by Ausgrid. So if I just charge my battery during the off-peak pricing period and discharge during the peak pricing period, and then the shoulder pricing period, the linear program sort of tells me how much to charge or discharge, then we can make a lot of money, $988 per year, without doing any prediction. It's fairly straightforward, pretty simple. However, the question remains, is this a good thing to do for the grid? So to answer that, on the left, we have a nice sunny summer's day and a customer who has excess PV generation as shaded in red. So if this customer installs a battery and uses our linear programming algorithm, our optimization algorithm, to schedule its charging and discharging based on the time of use profile, then we just move the red shaded area that we had for the PV generation to the peak pricing period. And now let's look at a winter's day on the right. This customer doesn't export any power to the grid without a battery, but with the battery, we now see some red shaded area. And so we're creating a new problem for the grid. That is, the red shaded region depicts the area, depicts the excess generation that potentially leads to significant voltage rise in the electric grid, especially when all customers install battery storage and look to increase their savings by way of following a time of use tariff. So we potentially create a new problem in the grid by installing battery storage and following such a time of use tariff. Next, let's look at our formulation. Let's look at a new formulation that would help the utility flatten the load curve, reducing the occurrence of reverse power flow in the grid. We formulate this problem with the following minimization expression, where X2 is the power delivered from the grid to the customer in the positive direction or vice versa. H here is a weight which we can select to preference the minimization at different time intervals. Now, our constraints include the power balance equation, meaning that we need to predict the day ahead load and PV generation. So we need to predict the load and PV generation. That is, we need to know what's happening on the grid in order to include the utilities benefits. So let's formulate this problem as a quadratic program, which is just an optimization problem. And we select H to be all ones, and we input the day ahead load and PV generation. The output of our quadratic program is a flatter grid profile as we expected. That is, for our program, we give the battery constraints to the program, the day ahead load and generation profile to the program, and our usable selectable H matrix, which we make just all ones. And the output is the power to and from the grid, which is X2, and the power from the battery, which is X1. So for example, in the figure, the top figure includes a red line that represents the day ahead PV generation, and the black line is the day ahead load. The second figure from the top includes a black line representing the power to and from the grid, and the blue line represents the power to and from the battery, X1. For the case where we have no battery, that is C equals 0. The third figure from the top, here we have a 1 kilowatt hour battery, so a very, very small battery. And we see that the grid profile, particularly in the late evening, is reduced, and the reverse power flow is less prominent in the middle of the day. In the bottom figure, we consider a 10 kilowatt hour battery, and we observe a flattened load profile depicted in black. However, the charge constraint of 1 kilowatt limits the peak load reduction from 4 kilowatts to 3 kilowatts at the end of the day, so midnight. So here, I alluded it to a little bit earlier, but we can see for this particular customer, the peak happens at midnight. Anyone recall why we get a peak at midnight here and not at like 6 o'clock, which is when the utility congestion peak usually hits? Anyone remember why some customers have peak loads in the evening?
Yeah, a comment come through about hot water, hot showers.
Yeah, fantastic. So the hot water system is heating up at that time, but no one's actually using the energy, right? So it's just heating up and storing the energy. So for this particular customer, they have their hot water system that turns on at 11:30, just before midnight, and heats up, as we can see in the early hours, until about, say, 2 a.m. there. And so that is not usually a concern for the utility because they can control that load, they can move the time that it turns on and off, and it's usually staggered with other customers to increase diversity. But the utility congestion point is usually between 6 p.m. and 9 p.m. when customers all come home from work, they turn on the shower, turn on the televisions, for example, the lights, they cook dinner, and particularly in summer, turn on the air conditioner, which really drives our peak in the summer period in New South Wales. Okay, so now let's move on to putting these two things together. So let's look at ways that we can balance the customer and the utility benefits. So we looked at a linear program, an optimization problem that just followed the time of use tariff to make profits for the customer, but it caused problems for the grid. And then we looked at a way that we could help the utility by just flattening the load profile. So not looking at profiting the customer, but just helping the utility. And in this new formulation, this new problem, we'll put those two things together and we'll introduce a weight, W, where we can balance those two things. So this is, we're looking at maximizing our savings and flattening the load curve. So if we do that with our new problem formulation, and we look at 145 customers from Ausgrid, if we select the weight 2, W to be 2, so the balancing of the customer benefits and the utility benefits, we see that most customers save approximately $800 a year, which was down from $988 if they just looked at making a profit. However, some customers actually lose money on some days. For example, customer A above loses more money than he makes from using the balanced QP approach. So we touched on this a little earlier. Anyone want to hazard a guess why customer A loses money from battery storage?
No comments at the moment, Elizabeth.
No comments? Okay.
But
So
question.
Sorry?
Interesting question. I'm keen to hear the answer.
So the reason for this loss is that customer A uses very little energy during the evening, during that peak pricing period, and has a very high off-peak energy consumption. That is, this customer is already doing good things for the grid with a low peak pricing load consumption and a high off-peak load consumption. So a battery has very little benefit for this particular customer when they're looking to help the utility and balance their profits. But on average, the most customers do save money. So we always have outliers, and we have to consider the fairness question of any policy that we bring in. And if we brought in battery storage, customer A would actually lose money from following such an incentive. So it absolutely makes no sense for this customer to install a battery. So we have to be very careful and mindful of fairness when we introduce particular policies. And hopefully you'll be alluding to that in future sessions, right? This fairness question that pops up as we go throughout the course. Okay, so now let's look at the utility benefits comparing the linear program, so the way to just make money for the customer, compared to the balanced QP approach where W equals 2, which profits most customers. Most customers save about $800 a year, but some customers, outliers, actually don't benefit from battery storage. So in the grey line here, we see the problem of reverse power flow, which we observed with the linear programming. So we're looking to make money, has been resolved on both the summer's day and the winter's day. That is the excess solar PV generation to reduce congestion during the peak pricing period in a way that limits reverse power flow. So that is, we have flattened the load curve. However, we observe here a rebound peak during the evenings, during the off-peak pricing period. So this is a result of the battery charging up really quickly in preparation for the next day ahead. So again, we have to be aware of new problems popping up. So we resolved one issue. So the grey line here is balancing the customer and utility benefits. And we can see there's no red shaded area. The grey line resolves that issue of reverse power flow. However, we do see a new peak popping up from battery storage beyond what the black line was in both the linear program and the quadratic program. And that's because the battery has to fully charge back up by midday in preparation for the next day. And so again, things like staggering the time when you start the off-peak or the peak pricing period, or the battery algorithm when it should you could potentially smooth that out with a different kind of algorithm would resolve that issue. But the key point is to always be aware of whatever you do that you don't create a new problem somewhere else. Okay, so now going back to our figure and a single customer with a linear program, a customer saves $4 per day. So, and that is like just to looking at maximizing their savings without any regard to the utility benefits. And with the quadratic program that looks to balance the customer and utility benefits, so it resolves the problem of reverse power flow and voltage rise, and also enables the customer to profit, we see that the savings are reduced from $4 to $2, but we're still approximately $2 a day with the time of use tariff as reported by Origin Energies. So we can still make money. It's comparable to the PV array, but we just reduce our savings by a small amount, or not too small, I guess, from $4 to $2. Okay, so, but this sort of leads us to a question: what if we had an electric vehicle battery instead of, for example, a Tesla Powerwall? So a Tesla Powerwall is a stationary storage device. You install it in your garage and it just always sits there, and it's about 10 kilowatt hours. There's some that are a bit bigger, some a bit smaller, but that's sort of like approximate range. Instead of that, we could look at electric vehicles, and in this particular context, let's look at the average EV customer who travels 40 kilometers a day and requires 5 kilowatt hours a day of power to support this. And the battery can be charged and discharged into the grid. So we have vehicle to grid enabled EV storage. So again, our approach is to consider the benefits of EV battery storage in the context of financial policies such as net metering and feed-in tariffs when customers are billed according to the time that they use electricity. So what is the cost or benefit of using a vehicle-to-grid enabled EV battery? This question mark we'll come back to in the following couple of slides. First, let's investigate the charging infrastructure and the time of day that the EV owner prefers to charge. As illustrated in the figure, most EV customers prefer to complete their battery charging from 11 p.m. to 7 a.m. or otherwise overnight when the solar PV generation is unavailable. Also, the preference is to use a level 2 EV charger that can charge the EV at a rate of 7 kilowatts from a single phase, providing a driving range between 20 and 100 kilometers per hour. However, we observe that there's still some customers with a preference for daytime charging. So for example, if you're a shift worker, you might be working at night and driving home and wanting to charge through the day. So we always need to be mindful of edge cases. So recall, on the left, we see the daily demand profile for 26,000 Australian residential customers. All these customers have installed solar PV with a peak combined generation output of 36 megawatts. On the right, we see the impact of the demand curve as a consequence of solar PV generation and EV charging. Specifically, EV charging increases the peak load in the evening, potentially creating new congestion problems on the grid, which might create the need for grid expansion. So hands up if anyone has an idea of what I mean by grid expansion. What might grid expansion look like? Have we got any takers?
One comment came in of reconductoring.
Yeah, fantastic. Reconductoring, so we can make conductors bigger. Expansion might be also upgrading a transformer, and transformer upgrades are particularly expensive. That's usually the most expensive upgrade, because if it's particularly in a substation, for example, the cost of that and transformers at high voltage can be over $1 million. And so conductor upgrades are one. Transformer upgrades, sorry?
Loop connections have come in and transformer upgrades.
Loop connections, transformer upgrades. What do they mean by loop connections? So making a mesh network, is that what they mean?
It's not, yes, that's what they said, making a mesh network, yeah.
Yeah, so in distribution, we typically have a radial network, but we have in the past had mesh networks, but we tend to open switches. But an upgrade might be simply, as you suggested, like changing the location of that switch. But in a mesh network, it's even more costly, again, because of the protection required in mesh networks is significantly higher than it would be in a radial network when we're looking at distribution grids. So yeah, interesting point there. And I guess that gave us a chance to highlight the cost of protection systems as well with upgrades. So there's many ways to expand. Typically, we look at expansion because of thermal constraints. So the transformer getting too hot, the conductors sagging too much. And we can resolve that by switching it out for a higher thermal rated capacity, or we could have voltage constraints. And ways to alleviate voltage constraints could be to have tap changing transformers, to put capacitors in as an upgrade, or it could be reconductoring, like we said before. So the additional thing there, I guess, is the tap changing operations or the voltage regulation equipment, and some new equipment to do that could be things like inverters, for example. Okay, so before answering the question of what is the cost or benefit of using a vehicle to grid enabled EV battery, let's first investigate ways to grid connect EVs to reduce potentially costly EV charging congestion peaks. Okay, so now that we have established that there's a financial benefit, okay, so now that we've established that there's a financial benefit to operating residential battery storage under existing tariffs, let's look at ways to coordinate residential energy systems to reduce grid congestion, to better leverage available PV generation, and to improve grid resilience to unforeseen events, including natural disasters. But first, I'd like to acknowledge my collaborators here, Professors Stephen Weller, Chris Kellett, and for the electric vehicle work, my PhD student who's just completed Nanduni, and collaborators Chetarika, David from Data 61, and someone from the University of Melbourne. Okay, so let's consider the coordination of residential battery storage to reduce the risk of critical failures in our grid, specifically the risk of widespread blackouts and or the risk of overloading critical infrastructure like the transformer that has caught fire here. So for example, if we represent the poles and wires, or otherwise the electrical distribution circuit with the graph, as shown on the right, and we identify a piece of equipment as limiting power flows across the circuit, then we define this equipment or this edge as the edge of interest. We highlight the edge of interest in red, and the power flows across this edge are denoted by X2. So in the graph, the gray shaded box is a microgrid, and the leaves of the graphs, that is nodes 1, 2, and 3, are the residential customers with energy systems as we introduced earlier. So now, can we use residential battery storage or electric vehicles to limit power flows along this critical piece of equipment, for example, a transformer? Again, we formulate this problem in a very similar way, but here instead we have a capital X2 representing the power flows along the edge of interest. Here all capitals represent the aggregation of power flows of all customers. So what's new is the power flow constraint across the edge, which we highlight in red. So to see how effective this strategy is, let's look at a case study using a GridLab D model for Element Vale, a realistic distribution circuit made publicly available by the utility OddsGrid. Hands up if you've heard of the platform GridLab D. Have we got any takers?
Anybody heard of GridLab D? I don't see any hands, Elizabeth.
Okay, power flow simulation studies are usually static. Whoop.
Your sound has cut out, Elizabeth.
I cut out. Can you hear me?
Can you hear us?
Yes, can you hear me? You can't
Yes,
hear me?
I can hear you both. Thanks.
Oh, fantastic. Okay.
Not sure if you can hear us, Elizabeth, but I can't hear you right now. Can anybody hear Elizabeth?
Probably something wrong with your connection, Tarek, because we can still hear Elise very well.
Okay, sorry, everyone can.
Okay, I'll keep going, but I'll note if you can't hear me. GridLab D is a quasi-steady state simulation platform that's open source, so anyone can download it. Created by PNNL, the labs in California, that allows us to do power flow simulations in quasi-steady state real time. A lot of platforms are quite expensive, utilities use for planning, and they're static. GridLab D and OpenDSS are the two open source versions that are available to researchers for free, that go beyond just static power flow, that do quasi-steady state. And so as part of a large $100 million grant to the utility OddsGrid back in 2010, they looked at GridLab D as a platform to do some simulations for the grid, to look at the impacts of PV generation and battery storage. And as a consequence, they made this Element Vale model, which is one of the most statistically average power flow models for Australia. That's why it was selected, available for us as researchers to do some analysis as well. And so this model goes from the zone substation, we call it, so the 132 to 11 kV transformer, all the way through the distribution feeder to the what we call the distributors. So from the 11 kV to 415 transformer to the customer's home, which is the distributor there. So it's a network usually that you have available just looks at one voltage. This looks at the low voltage, the 240 volts, the 11 kV volt system and connects in the voltage reading in from the 132 to 11 transformer. So it's the most sophisticated model I've seen, and it's publicly available. And so with this model, we adapted it to have a 50% penetration of solar PV. So 50% of customers were modeled with solar PV and battery storage. And there's 1,785 customers that are connected to the feeder. 845 of these customers have solar PV plus a battery. That is, the PV penetration is above 50%. So here our edge of interest is the 132 to 11 kV transformer, because that transformer is quite expensive to upgrade, and it is overloaded during one of the hottest days in the year, which we'll look at in a moment's time. So air conditioner load was driving the peak. So now let's look at scheduling battery storage with receding horizon optimization. So what a receding horizon optimization does is the same as we were doing previously. We solve an optimization problem for the day ahead, but instead of deploying the battery charge and discharge for the day ahead from that particular algorithm, we just deploy the first instance, and then we solve the problem again for the day ahead. So moving the window for the day ahead every half-hour interval. And what that does is let you smooth down that rebound peak that we've seen earlier. Okay, so the top figure here shows the case when batteries are not scheduled. So here we see the peak load along the distribution circuit is approximately 6 megawatts. And in the bottom figure, we implement receding horizon QP energy shifting, so balancing the customer and utility benefits, which reduces the peak load from 6 megawatts to 4 megawatts. Typically, this peak load reduction of 2 megawatts is enough to defer capital expenditure of the transformer capacity upgrades for many years. So for example, in some rural areas, 2 megawatt reduction in peak load could defer the need to expand the transformer, which would cost in the order of $1 million plus by approximately 10 years historically. So with such a transformer costing over $1 million, 2 megawatt reduction is a really great job. So the batteries are doing a fantastic job. So we're charging and discharging everyone's battery in the same way to reduce the cost for electricity for those customers, and to reduce this peak load that we observe during the very hottest day of the year that happens like once every 2 or 3 years. So a very rare event. Anyone want to hazard a guess at the conditions around our peaks in summer in Australia, our peak load? What drives that peak of 6 megawatts? Have we got any planners in the room? Oh, I can't hear you. Tariq, I think you're on mute.
Okay, some ideas are coming in, Elizabeth. One is about the use of air conditioning. A couple of people have suggested that.
Yep, perfect. So when I was a planner and had my hat on for that, usually it was after the school holiday period when people were back from work. They all come home from work, they all turn on their air conditioning, they all cook dinner, they watch TV. It's too hot to go out, so everyone's home using electricity. And it wouldn't be that one day of the year that it would happen, it would be during a heat wave. So the first day that happens, not too bad, but it's usually when the heat wave lasts 2 or 3 days, so 3 days of over 40-degree heat. By the third day, everyone's just over it, right? Anyone that was thinking, oh, I can handle a little bit of heat, I'll just turn my air conditioner off, by the third day just leaves it on. And so that usually was the condition for the very worst case scenario of driving out peak loads. But that was like more in an urban setting. And if we look at more rural settings, some of the things that drove the peak loads were droughts. So irrigation pumps would drive it, or holiday areas. So for example, there's a nice, beautiful holiday spot, which we call Nelson Bay on the mid-north coast. And everyone used to go there for New Year's. So if we have a 40-degree day and it's New Year's Eve, this like city that swells about 10 times the capacity, that would drive, for example, the peak. So it's very regionally specific. But for New South Wales, Ausgrid, it was absolutely the air conditioning that was sort of the killer in general across the network in terms of driving peak load. So here, the top figure shows the case when batteries are not scheduled. We see the peak load along the distribution circuit is 6 megawatts. In the bottom figure, we implement the receding horizon QP energy shifting approach. So we reduce from 6 megawatts to 4 megawatts, the peak load, and we defer capital expenditure. But what about the supply voltages? Does fixing the central problem also fix the local voltage issue? So for this feeder, supply voltages must be within plus 10% and minus 6% of the nominal 230 volts. So Australia and the East Coast, 230 volts is our nominal voltage for supply. And we want to keep that within a band of plus 10% and minus 6%. And so previously we're looking at scheduling everyone's batteries in the same way to reduce the peak load condition. But what does such a solution do in terms of supply voltages? To answer this question, we'll look at the impact of supply voltages and we'll zoom into the substation highlighted. So here we zoom into the customers connected to the supply transformer HP1431. And in the top figure, our baseline, we observe voltages when no batteries are installed along the feeder, noting 50% of the customers along the feeder have connected solar PV. Specifically, we observed that 23 out of the 37 customers connected to this distribution transformer have voltage excursions outside our allowable limits. In the bottom figure, we implement the centralized receding horizon QP energy shifting approach. So we're balancing customer and utility benefits, and we're scheduling everyone's battery in the same way. And by doing that, we can reduce the number of customers with voltage excursions down to 14, but we don't eliminate all of the voltage excursions. Anyone want to hazard a guess why we don't eliminate all of them? It's a common thread we've had previously. Why do some customers still have voltage excursions? You'd think if the average and we've reduced the peak load, why do some customers actually suffer, I guess, from following such an approach? Like, so if you have a voltage excursion, your inverter switches off, which means you don't profit from making that solar energy. So 14 customers would have voltage excursions, which would create an inverter trip, for example. No takers on why? Nope. So some customers aren't average, right? So some customers don't all come home at 6 o'clock, turn the air conditioner on, cook tea. Might have shift workers, for example. They go to work at 2 o'clock and come home at midnight, right? And so they're following a very different profile, a very different tariff. Batteries might actually not be useful or beneficial to them, as we've seen earlier. So we always have some outliers. And so solving central problems don't always solve our local issues because no customer is average. They're all a little unique. Okay. Basically what average means is like we all have the same behavior, right? So when you eat lunch is not the same time as the next person next to you eats lunch. Like, you know, on average, we might all eat lunch in the same sort of time zone, but then some days you might skip it and have a later one or an earlier one, or you might, I don't know, just decide to go on a diet and not have lunch that day. Who knows? But we're all different. Our behavior is different. And so the grid is the same. Everyone's behavior reflects, that difference in behavior is reflected in our electricity. Okay, so now let's switch to customers connected to this transformer, to a local approach to energy shifting. So let's balance the customer and utility benefits, but let's use their local information to make the decision. So their load and generation that they produce locally instead of the centralized global load and generation, as previously described, and we'll use a weight of 2. So in the bottom figure here, we observe that all customers have voltages within range when implementing the approach with a local approach. So we're using their local generation, their local load to do the balanced approach, and we resolve all the issues. So the key takeaway here is that solving central problems does not always solve local problems in a distribution grid, which motivates us to include a grid model in our problem formulation. So before introducing a grid model in our problem, let's consider the more challenging case of coordinating EVs, which, as we observed earlier, can exacerbate congestion peaks in the grid, creating new voltage excursions. That is, we connect our residential energy system with EV and rooftop PV. to an electrical model in a distribution grid. And we investigate the ways to coordinate EV charging and discharging to improve grid voltages and to reduce grid congestion peaks. More specifically, let's look at maximizing the customer benefits, similar to our previous linear program, where we looked at just maximizing the customer benefits based on the time of use pricing, subject to the EV battery constraints and the voltage constraints along the distribution circuit. So here, our formula here is the voltage constraints along the circuit. This is quite an expensive thing to incorporate into the optimization program in terms of time it takes to solve and complexity and scalability of doing such a thing. So we need to include it if we want to solve a central problem and a local problem together jointly. And make sure we resolve all issues, but there is a challenge of scaling this to like millions of nodes, which is what our distribution grids typically have. So for a single customer, we observe it is possible to reduce EV charging costs from $9 a day to 72 cents a day with coordinating EV charging and discharging. But note that now we have included the grid constraints in the problem and not all customers profit equally. So in our previous central approach where we all charge and discharge EV batteries the same way, all customers made the same profit. But now that we've included the grid conditions and some customers live close to transformers, some customers live far away. If you live closer to a transformer, you're more likely to have a good voltage than you do if you live at the end of a feeder. And so consequently, we introduce a fairness problem into the problem by incorporating voltage constraints that are local. So that is, customers with underlying voltage problems will profit less than those with no underlying voltage problems if they both follow the same EV charge and discharge profile. Furthermore, we observed that the peak load of 9 kilowatts with uncoordinated EV charging, so they're just charging and discharging based on the price, when they connect with no consideration of coordinating amongst themselves. So we reduce that peak load is reduced to approximately 5 kilowatts with coordinated EV charging and discharging. So they all follow this algorithm. But what about our supply voltages? So if we just charge and discharge, so if you just charge and discharge and we took away the voltage constraints, then we would have this 9 kilowatt reduction to 5. So we solve the problem of upgrading, for example, the transformer. But what about the supply voltages? So if we don't include the grid model, so the voltages for each customer, we see in the figure here that the feeder voltages are below the lower bound of 0.95 per unit when EVs charge according to the time of use tariff in the absence of grid constraints. And the voltage excursions like this will switch off the EV charging for safety reasons. So we need to include the voltage constraints is basically what that's saying. And so in contrast, when we do that, we include the grid model and we include the voltage constraints. In the figure, we see the black line representing the algorithm, which incorporates the grid model and the constraints as highlighted in red. And we observe that the corresponding supply voltages remain within permissible thresholds as highlighted in red. And in this way, the algorithm accounts for unexpected EV arrival and departures and errors in the day ahead non-EV load forecasts. So that is, the voltage excursions that we observed here are a consequence of the day ahead EV charging and discharging, as unexpected EV arrivals and forecast errors cannot be accounted for in the algorithm. So going back to our figure and a single customer, EV charging can cost that customer $9 per day for a driving range of 110 kilometers, depending on the time of use tariff. However, if this customer coordinates the EV charging and discharging, we can reduce the cost of to approximately 70 cents per day with a saving of $8.30 per day. But this figure will depend on where you connect to the grid and if there's any underlying voltage constraints. Okay, so before we move in to the last section of today's talk, where we'll discuss new control paradigms, I'd just like to pause for a moment and see if there's any Q&A and give everyone a moment to take a sip of water. I know we'd be going for an hour and 20. We probably all just need like a couple of minutes and then we can maybe think of some questions and come back in about 2 or 3 minutes. Does that sound okay to you, Tariq?
Sounds perfect. Yep.
Wonderful. So collect your thoughts, pop some questions in, and we'll give everyone a couple of minutes to do that.
While people are typing in their questions, Elizabeth, there are a couple of questions that we didn't get to that have been popping up in the chat.
Oh, fantastic.
So, like from earlier on. So one question was about, obviously you've done this analysis for Australia, and it's based on a difference in the time of use tariff between peak and off-peak times. How big is that difference? Somebody asked the question, how big is the difference between the peak load price and the off-peak price?
Oh, it varies. So we've deregulated our energy markets. And so there's many different people you can buy electricity from. So for example, in the ACT, we have actually 2 peak pricing periods, one in the morning and one in the evening. Whereas those ones at Ausgrid were just for the evening. So that was their traditional congestion peak that they're experimenting with changing. And for me, as an example, I could just not even have a time of use pricing tariff. So I recently installed solar and we didn't have a battery. And so I just had a flat tariff rate of 19 cents per kilowatt for energy I used. And I think a 9 cents was really great feed-in tariff. But we've recently put in a battery. And so now it makes more sense for us to leverage the time of use tariffs. But what's even more exciting that we can do, if you've heard of virtual power plants, we're now subscribed to the Tesla virtual power plant. So what that does is charge and discharge your battery to help the transmission grid, for example, frequency regulation to balance the supply and demand. However, some of the issues with doing that is that we're solving a central problem. So frequency is like global, a big problem, but we're trying to use local resources that are constrained by voltage to do it. So I don't believe any VPPs have adequately resolved that problem, because the grid network that you'd have to include to do that is quite extensive, and it's quite a large and probably not possible to do in real time. So going back to the question, the differential in price, so we went to the time of use tariff. I think it's now 36 cents peak, and maybe the off peak is just like 1 cent below what we were paying for our just flat rate, right? So, but we get some bonuses for doing that, because we allowed the utility to use our battery up to 50 times per year. But yeah, there's a big range, and you have to like investigate. And then also in the US, where they have in some states time of use pricing, not everywhere. So they have time of use net pricing in a couple of states. Again, I think there's a lot of diversity on utilities. Even within a state, there can be many different utilities operating and offering different prices. And then there's separately, which we haven't spoken about today, capacity pricing. So the US has a lot of utilities offer capacity pricing. So the more energy you use, the higher the price, not the time that you're using it, but the amount that you use. So people that use a higher amount of energy pay a larger price for that compared to a lower amount of energy. Again, equity comes into that, because usually, particularly when we looked at it at Ausgrid in Australia, with time of use pricing, we always allowed customers to opt out of that because of fairness. So customers, for example, elderly who have retired, are at home using energy in the middle of the day, and their bills went up considerably with time of use tariffs, and they couldn't not afford to install the latest appliances which were energy efficient. So having a really old fridge, for example, and old appliances would increase their bills compared to other people that could afford to buy all the modern appliances that were more efficient and have timers and controllers to schedule their loads at different periods. So underlying fairness questions sort of are teased out. I think that was a very long answer to a short question, but is there any more as we're waiting?
Well, a follow-up question on that. I mean, that your answer there makes clear that, it's this having the time of use tariff or differentiated tariff structure is key for exploring or seeing some value in these kinds of solar battery systems. What about the demand, the consumption behavior? You're also presenting analysis from the Australian perspective, but in some of the countries that our colleagues are working in Indonesia, in Vietnam, and Philippines, the consumption behavior, the load profile itself could look quite different. So how sensitive do you think your results would be? Like how would things change if the behavior is changing?
Yeah, so from the algorithm, nothing would change. You just have to input basically the load that you have, and it would schedule the battery accordingly, like as long as you have some time differential in price. So the analysis is looking at time-based pricing, not capacity pricing. A different algorithm could look at capacity pricing, and I've published a paper with some colleagues in San Diego looking at that. So not too distinctly different, but essentially even within Australia that I've looked at it, as I've alluded to, peaks are different, loads are different, customers are different, behaviors different, and seasons and temperatures sort of drive a lot of our peaks. But regardless of those days, those customers, those peaks, those seasons, there's just one algorithm that solves it. And so as long as you can give me the load characteristics for your particular country or where you're located and the price, then this algorithm works universally. And I would imagine diversity popping up. The only thing that I would say that I'm aware of is that there's a lot more, as we do in Australia as well, have a lot more rural microgrids, so disconnected from the utility. And so they're like companies like Bbox that I'm aware of that operates in Africa, and there's it's eluded me the name, the ANU startup, I guess, that operates I think out of Cambodia. But there they look at DC grids, right? So they're looking at providing energy with PV and battery just to apply really essential services like just lighting in rural remote areas and things maybe for cooking, whereas refrigeration is not something in that is considered necessary in all countries, right? So I have colleagues in Sri Lanka, for example, where they cook their food each day and they don't store it in the fridge and reheat it like we do. They have it fresh daily. So but yeah, so as I would say, it depends on the country you are and the profile, but if you're connected to a grid and you're looking at reducing peaks for a utility, and pretty much every major city has a centralized grid. It's just when you go out to remote areas that there's usually microgrids, and then sometimes they can be DC, then this is the approach that you can take. It's an optimization-based approach. You could do heuristics, so rules-based approaches, and achieve something quite similar.
There's, Elizabeth, I think there's two more quick questions to ask. Okay. So one question follows on about your algorithm there, I guess, and the question is, you've been describing the kind of the situation for rooftop solar PV operations, but could you apply the same kind of approach, same kind of modeling, to look at grid congestion from solar farms, like feeding into the grid, for example? So
absolutely, yeah, and again, the same algorithm applies, right? They're just a large customer. So we sort of started with the residential setting here because it was the residentials, like the customers that were driving our renewable energy transition. So it was the government's not at a federal level really driving it, but states with really encouraging incentives, like we had a 66 cents per kilowatt hour feed-in tariff in the early 2010s that sort of made customers, even if they weren't as mindful of climate change and what they needed to do to help combat that, but it was just purely financially driven, their decision to install solar PV, because all of the energy, it was separately metered, so all of the energy that they produced was they were paid 66 cents per kilowatt hour for, and that was so successful they had to shut it down within a couple of months because the cost of that program sort of blew out quickly. And so as I said, yes, I just see a wind farm as just a large individual customer. Again, you could have an edge of interest that's at some remote distance away from the solar farm, or you might be constrained at the solar farm for how much energy you can push back into the grid. And so, battery storage would be a way to enable you to have a more regular energy delivered back into the grid without this peak and trough, and potentially save some more money.
Yep. And last quick question, Elizabeth, is relating again to thinking that in some of the countries' context, there isn't lots of battery storage and EV, but there is a growing number of electric bicycles and electric cycles, and, motorbikes and so on, electric ones.
Mm-hmm.
And the question is, you mentioned that, if there's just one or two households that have it, it's not a problem at the grid scale, but as the number grows, it can become a problem. So is there some kind of threshold, like at 50% of residential customers having solar PV with battery, or some other percentage where you start to see this becomes a problem for distribution utilities?
Yeah, and that's a really great question. And I also want to just clarify, 50% isn't the magic number for Australia. It was just that particular feeder where we looked at 50% penetration that we had particular issues. So in California, they had a 20% rule, where anything over 20%, then they would do an investigation, a planning study. They've looked to eliminate that or have eliminated it. But it really depends, as I said, locally. Every region within a distribution network is different. As I said, holiday areas have different peak profiles, different congestion to rural areas with irrigation pumps, for example, to urban areas. And even within an urban area, they can be locations with older equipment and appliances. So there are houses that are much older versus newer estates, newer developments. And so there is no magic number of when it becomes a problem. And that's, I guess, what a lot of research is happening at the moment, to look at how do you facilitate all of these things with like an envelope that's dynamic and changes with time, so you can sort of set and forget it without doing these exhaustive desktop studies, which is what planners typically do to identify when it isn't an issue. So absolutely, the problem of diversity. So if everyone has that electric bike and they all charge at the same time, then most likely there'll be an issue at some stage. The question is, when is that stage, and is that the main contributing congestion point, or is there something else that's creating a greater congestion that will drive network expansion? And so no silver bullet, I guess, in terms of the answer there, but an interesting question to study. Keeps me in a job for a while, I think. Okay, shall we move on? Have we given everyone a chance to regroup? Fantastic. Okay, so moving into our last part of the talk today, I'd first like to acknowledge my collaborators here at UC Berkeley, the University of California, Berkeley, including Professor Sasha von Meer at the University of Michigan, including Professor Dennis Bernstein. And for this, some of this work, we were funded by a grant from the Department of Energy under the Energize program. And our project partners are listed here, including GridBright, Pacific Gas and Electric, Berkeley Lab, and Opal RT Technologies, and Doosan Grid Tech. This was particularly this phase-based control, which I'll be talking about shortly, was a project funded between 2017 and 2020 with 2.573 million. And it was really looking at that problem that we sort of just discussed of how do we look at controlling the grid when it's difficult to have the model to understand all the voltages. It's difficult to know when things become a peak. How can we rethink the way we control and operate the grid, so we don't have to do these exhaustive desktop studies, as I was just alluding to? So, how can we control the grid so anyone can connect any appliances? We don't have to look at, how many EVs, when does it cause a problem, and when do we sort of switch over our control of those devices, but have a new control paradigm that enables us to do all of those things within it. Okay, so to motivate this new control approach, which we termed phaser-based control, let's first define a synchrophasor. So a synchrophasor is a time synchronized measurement of the voltage magnitude and the phase angle at different locations in the grid. In the transmission grid, the phase angle difference between the two voltage waveforms as measured at two synchronous generators is what drives power flow according to the equation in the slides. So the picture here depicts a microsynchrophasor, which is precise enough to measure very small phase angle differences in the distribution grid. And this microsynchrophasor is what we commercialized with the team in Berkeley, and what allowed us to rethink how we might control and operate the grid so that we're agnostic to the devices, so air conditioner, PV, electric bikes, that we can just control the grid to facilitate the connection of all of those devices in a particular way that manages our voltage constraints and our thermal limits and allows us to do real-time control. So this new PBC, we call it phasor-based control paradigm, has a supervisory layer and a local layer. The supervisory layer is responsible for assigning phasor targets throughout the grid according to some optimization criteria. And the local layer is responsible for tracking the phasor targets assigned by the supervisory layer. In this way, the local layer does the real-time control, and the supervisory layer updates set points throughout the grid on a timescale that's appropriate. So if it's a really large problem and it takes hours to solve, that's fine. The supervisory layer takes the time that it needs to solve the problem. And while it's updating that, the local layer does the real-time control through set points. And it's designed in a way that we don't violate any constraints. So importantly, instead of assigning an edge of interest, like we looked at earlier with that red line and constraining power flows across it, so for example, a transformer, and we just constrain the power flows across the transformer, we can now assign voltage phasor targets at the nodes. So for example, node 11 and node 6 to achieve the same result. So hands up, what would happen if I assigned a voltage phasor at node 11 to be equal to the voltage phasor at node 6? Anyone want to hazard a guess what would happen if the voltage phasors at both nodes 11 and 6 were the same?
Any takers who want to put up their hand or make a suggestion in the comment box? What happens if 6 and 11 were set the same? Maybe you'll have to help us, Elizabeth.
No worries, but good to have a think about it. So if our voltage phasors were the same, we would have no power flow at all across that line. And so what we've done is created a virtual switch essentially for our grid. And so that gray shaded box could be considered then a microgrid within a larger grid that could switch in and out without a physical switch, right? And so by assigning voltage phasors or set points at different nodes, we can control the power flow. And if they're equal, we send that power flow to be equal to 0, right? So we can either constrain power flow in megawatts, or we can set voltage phasors to constrain power flow across particular edges. And so, so there's a lot of different things that we could do with the supervisory layer. So if the supervisory layer assigned those two phasors to be equal, then we could adaptive island. If it set them to be in a way that restricted power flow, we could do the same as that we did before. Like, for example, reduce the power across the transformer by 2 megawatts. Okay, so specifically for the supervisory layer, we can set the objective to align phasor targets to drive the power flow across the edge of interest to 0, or we can assign the phasor voltage phasors to balance each phase across, so the power flow in phases A, B, and C are equal. Our constraints are, again, the power flow constraints, the voltage constraints, and the battery constraints. So here's an interesting point, maybe that we can get an answer from the audience. A particular difference between the US and Australian distribution grid is that in Australia, we have 3 phase. So a customer can be connected to a single phase, say phase A, or 2 phases, A and B, or 3 phases, A, B, and C. In the US, they have a split phase transformer, which means that it's not clear if you're connected to A and B, like there's a coupling across that, right? So a split phase transformer, if I draw it, means you can be connected to B and C, but it's not just B phase or C phase, it's a combination of those. And then that's 120 volts to neutral for each of them, or 240 volts from phase to phase. So you always have those two phases connected through the split phase going to a customer. Whereas in Australia, we can have just a single phase, two phase, or three phase, and it's not in a delta connection, it's like a star connection. So it's really easy to decouple each of them. Anyone want to give me a moment on, I guess, the distribution in your particular country? Is it a three phase that customers connected to, a single phase, two phases, or do you run two phase systems? Because they're also possible in some countries that they just run a two phase instead of a three phase system.
Any of the colleagues from Indonesia, Philippines, Vietnam want to explain a little bit the context in your country?
Excuse me, the chat is disabled. I cannot write on chat. Thank you.
Ah.
The chat is disabled. Oh, if one of the co-hosts, if anybody knows how to enable chat.
Thanks. Now it's enabled. Thank you.
Okay.
Yeah, so is it does everyone have maybe hands up? Does everyone have a three-wire system, A, B, and C phases? Hands up if you know, if you've got three-phase distribution grids, or if you have a two-wire system, a bit like the US, where you have just A and B or B and C that each customers can connect to. In the US, they only have about 7 customers connected to a distribution transformer, whereas in an urban area in Australia, we have up to 300 customers connected to it. So we have a higher voltage distribution circuit with three-phase connections, unless we've got some really unique areas in Queensland where we've got single wire earth return distribution grids where they're a little bit different, but I won't go into the particulars there. So anyone, hands up if you're aware, if you have a three-phase system. Do we have some hands up?
There is some comments in the chat there, Elizabeth, where there's, it seems to be both single and three-phase. So sometimes three-phase for commercial and residential, seems to be more single-phase. That's certainly what colleagues from Philippines and Indonesia are saying.
Okay.
But we have some hands up as well in response to your question from Vietnamese and Indonesian colleagues.
Okay, so do you want the hands up three-phase system, I guess? Anyone want to come off mute if they know of any issues with voltage because of the unbalanced nature of the, so if you have customers connected to a single phase, then you have to be very careful about rotating that single phase that those customers are connected to. Otherwise you could have an unbalanced system, and that unbalance could drive network expansion if not adequately balanced. Is that something anyone's aware of as a particular issue in the country? Unbalanced networks? Sorry?
In Indonesia, actually, in distribution side, we have like three-phase system, but customers can connect to either in three-phase or in one phase.
Okay.
So yeah, like before that, there is also issues in the voltage unbalance, especially when we have like a DC load, like a commuter line, and also sometimes we don't have we don't balance it properly for the customer to connect in the single phase when one single phase customer connect to the three single phase.
Yeah, so we have the same issue, and the US again also has that issue of balancing, right? And so one particular strategy that we're looking at with this phaser-based control was just how to balance the grid out, and by balancing it we could improve the efficiency of the operation of the grid so that we could avoid expansion, for example. So it sounds like that's a fairly universal across all the members here. We could have unbalanced networks with single, two-phase or three-phase connections. And so in this new paradigm, the supervisory layer could assign voltage phases to balance out the phase across A, B, and C, so balance out the power flow. And our constraints, again, in this paradigm are the power flow constraints and the voltage constraints and the battery constraints. So really great discussion there. Thank you everyone for chiming in. I know we're getting close to the end, so I'll look to try and wrap things up and give everyone a chance to maybe comment at the end. So just touching on this PVC paradigm, our local layer in the paradigm, we considered two approaches. First, a PI control, so proportional integral control scheme with offline tuning algorithms to track the phase references set by the supervisory layer. And the top two conference papers discuss this approach in more detail. Our second approach was called retrospective cost adaptive control, which is designed to re-optimize the control law over the trailing data window by using recursive least squares. And this re-optimized controller is implemented at the next step. This work was done with colleagues at the University of Michigan, in particular Dennis Bernstein and his group. So in this way, the approach is model free, so we don't need to know all the power line models, and the approach is designed to reject disturbances. So a disturbance, for example, something tripping in the grid could be considered a protection scheme operating could be considered as a disturbance. And the third publication here provides a few more details on this. So to test the performance of these approaches, we use physically meaningful experiments. We considered the IEEE 13-node test feeder, which represents an unbalanced distribution feeder. And we assigned performance targets. We used an OpalRT real-time simulator to test some of these algorithms at the Berkeley lab. So far, so good. So it's still early days in us developing and maturing this phasor-based controlled paradigm. But we've actually done physically meaningful experiments with real hardware, real batteries, PV connected to a simulated electricity grid in real time. Okay, so watch this space as we continue to develop this paradigm. And so lastly, I'd like to acknowledge some emerging work in a new control paradigm for operating microgrids during extreme weather events with a focus on resilient electricity pricing. In particular, the paper above, which was published by my PhD student Zanab, with collaborators Eugene and Guodong, who are at the University of Sydney, and Ian Peterson at the University at the ANU. Okay, so this work was motivated by the February 2021 Texas power outages, which were a result of extreme cold weather throughout the state. During this event, some Texas received power bills for US $5,000 or more for only 5 days of power use. Thus, our work was to design electricity prices for microgrids to ensure that the price is affordable, even during extreme weather events where the energy supply might be limited. So Texas is usually a hot climate. They had this crazy weather event which created freezing cold temperatures, and our work looked at ways that we could regulate the heating for a house when there was energy, and that you could set a thermostat and be assured that you weren't going to get a bill that was unaffordable for you to pay. So we look at user preferences. For example, I want my temperature to be 18 degrees Celsius. You set that, and then the algorithm goes away and figures out the price for electricity. So it's not a time of use price, it's like a real-time price, and it coordinates with all of the others, and it does it in a way that it's the best price for everyone, but it's also fair, so we don't get some bill shock in the days that come. Okay, so we propose, like, this essential scheme is what we call a transactive energy system, where customers buy and sell electricity from one another within a microgrid. And such customers are otherwise known as by the term prosumers. Our aim was to guarantee that the price for electricity at a competitive equilibrium is also socially acceptable, even during extreme weather events like in Texas. That is, the selling price, where all prosumers buy and sell electricity, is considered fair and affordable. The microgrid operations can be implemented in a centralized fashion, as is the image on the left, where you have a central coordinator for managing communications among the prosumers, otherwise known as agents, or it can be implemented in a distributed fashion, as in on the right, where agents communicate directly with one another via a peer-to-peer network. So this is all underpinned by a communication network, which traditionally we haven't needed to operate and control our grids, particularly with the earlier algorithms I introduced earlier. They're very low on the communication network, whereas this requires like a very extensive peer-to-peer communication network. And so some of our further work is looking at how ways to reduce the communication overhead with such a scheme. So our aim is to reduce customer energy bills or to maximize customer profits, subject to satisfying the thermal comfort of users while guaranteeing the price for electricity never exceeds an affordable price threshold, even during extreme weather events. In this way, the customer can simply set the temperature thermostat to a comfort level without regard for the need to monitor the price for electricity, as they will not experience bill shock, as the transactive energy system will always do its best to find the best price for energy for everyone within a reasonable limit. Okay, in summary, today we discussed a single residential energy system. We looked at ways to coordinate these residential energy systems, and we touched on new control paradigms for the control of electric grids with distributed actuation, for example, PV, battery storage, electric vehicles, and microgrids. Okay, thank you. And now over to questions in our last few minutes. Have we got any that I've missed, Tariq?
No, not at this stage. I don't see any other additional questions in the question box.
Okay, so maybe we can go back to the differences, I guess, between the networks that I've sort of described here and the network. So is there any questions, I guess, on how applicable this is to your particular country? Is there any questions that sort of come to mind of like what would work and what won't work? For example, Texas was an extreme cold weather event, right, that went to the price skyrocketing. I can't imagine like freezing cold conditions, for example. But maybe there is, like I know in the northern part of Thailand, it can get quite cool in the mountains. And in some parts, so have we got anyone, I suppose, on the call that has freezing cold conditions that drive the high electricity prices, or is it usually hotter weather that drives congestion in the electric grid?
Would anyone want to talk about the drivers of congestion in your national grids?
Or anything else? Feel free to pop in a question.
I think everyone has now graduated as an electrical engineer, Elizabeth, after this course. This is a really interesting deep dive into some of the technical issues.
Yes, and I hope you didn't get too caught up in all the maths. I hope the message and the communication was there, but I just like to provide that for those of you who would like to go away and tinker. So if you hop onto MATLAB and you type in QP like prog, then you can simply do some of these algorithms yourself. But all Python is an equivalent. They have like all of these optimization engines to solve these problems are becoming more widespread and easily accessible, which is really fantastic.
I'm conscious as well that Tang, you have a survey to do with colleagues here as well about the deep dives. So maybe what we could do is we could pass over to you, Tang, to do the survey and then take it from there.